this and live streaming it. So Marcelo's here helping me out. So if you have any questions, there's only a few of us, so just jump in and turn our mic off if you want to, and we'll see how it goes. Okay, I'm gonna share my screen here. I think. Sorry. Sorry about that. Let's try this again. Okay. Okay, I'm not going to go, you probably see my desktop here because I'm going to be doing some examples. So I might switch between them, the slides and terminal. If that's annoying, let me know and we'll adjust accordingly. Okay. Okay, Marcelo, are we recording?
Yes, Scott, we are live and recording.
Okay, great. Thanks a lot. Okay, guys. Well, welcome today. Today we're going to talk. My name is Scott Northrup, one of the analysts here at SciNet, and today we're going to talk about some parallel performance tuning. It's supposed to be a 3-day course. It'll probably be about 2 days. Definitely today we'll go over some very introductory topics about parallel performance, some serial performance, and then we'll overview some of the tools as well. So let's get started here. So, okay, so the thing about parallel performance, the first thing you want to do in any system to sort of figure out, where you're at is to do some profiling or figure out, some sort of metrics of how well you're doing. We all, you inherited this code, either you wrote it from scratch or you got it from your research group, and you want to figure out, well, how well am I doing? Is this code, is it a parallel problem? First of all, you don't know. These are complicated codes. You could have some GPU stuff in there. You could have a memory bound problem. You don't know. You have IO issues. So the first thing to look at is to come up with a scheme that you can actually, actually measure. So actually get some real quantitative data on. So there's a bunch of different ways to do that. And this first little bit, we're going to talk about a couple of different ways that we can do that. So in the common terminology for that is profiling your code. So actually instrumenting it in different ways, in different levels, and actually sampling as you go along and figure out, what is taking most time. Whether is it calls to memory, is it just CPU load? Is that what your bottleneck is? because you're like, oh, I'll just throw more cores at this. We get this at SciNet all the time. Somebody's take this code, says, oh, I'll just, it's got 40, I'll just run 80 cores, and then it runs not any faster than you had before. So obviously the performance is in a different spot than you thought. So this is about trying to figure out where that is. So it's just basically looking at where time is being spent. So just trying to find the most expensive parts of your code. Don't waste time optimizing parts that are not important. If you're spending all your time, there's a whole lot of ugly code at the beginning, but it's only reading that one data file once, and that's only 5 minutes of your 10-hour run. Well, that's not really where you want to spend your time. You want to spend your time is in your looping, in your main function, where you spend 99% of your time. And so that's where we want to find those bottlenecks. That's where we want to find it. If anybody wants these slides too, if they go to the main website, you can actually, I have a copy of them. They're put up under the files there. I think they're linked off the main page as well. So one of the simplest things you can do is basically just, without actually trying to instrument anything, is just using the basic time command. If you write just time and then a command on the command line, it'll basically give you a few pieces of information right away. So you want to set up your code, you make a change, you want to time it, you can easily do that. And it doesn't cost you basically nothing. So a lot of people in their code in your submission scripts and SciNet just have this to begin with, either call date and date or just call the time command. And it gives you some interesting, useful data. So this is just in serial, this will just be we're talking about some serial performance, not parallel performance first, because a lot of what you want to figure out is where that bottleneck is. And it may not be the parallel part of the code. It may be just in the serial part. So you kind of have to decouple that. So you have to kind of look at where the performance is from a serial point of view, memory, CPU, IO, and then also look at where the parallel part gets added on. Because every parallel code, if it's run with one processor, is a serial code. So what we're going to start is just using some of these tools first. And then from there, we can figure out how to look at just the communications part. So the time command, and you can use this on a parallel code too, but it's just going to measure the MPI run command on the one primary task. So it tells us information. So the overall, it'll give me the real, which is the elapsed wall time, the actual user time that actually my code did, and then some system overhead. And right away, this can give us information that's interesting. Ideally, the user and real would be as close as possible. That means I'm doing everything in memory and system, and I'm not wasting a lot of system time. If I make a lot of system calls, or I have a lot of heavy IO, that's going to show up in the system time. Okay. And so this is something relatively easy you can do. And then if you make changes to your code, especially if you have a good base case, you can kind of adjust this over time. Now, there's going to be a little bit of different variations, especially if you're running this on the login node, if there's somebody else doing something. But if you're running in a debug node where you have the whole node to yourself, this should be fairly consistent. Now, that being said, if it's a little toy code and it's only 2 seconds, well, if that's probably not enough to sample. You probably need, something, a significant amount of size. And we'll talk about what a good representative problem is to compare later as well. Okay, so that's just the time command, which is very useful. Another one, and most of you guys probably know a lot of this stuff, so I'll go relatively quickly, is the top command. If you type top or htop on the node, or you log into debug node, you can see your processes running. And right at the top here, you can see the percentage of CPUs. If it's a parallel code, if it's MPI, you'll see all the MPI tasks here. So here's one running across the multiple processors. If it's a threaded code, they'll be stacked together. And if you use the H command, you can actually see all the threads broke up. But if it's, say you were running on 10 threads and it's 100% each of them, actually show up as 1,000. You also can see your percentage of memory. But you can also see some interesting things here. Like in this one case, here you can see that there's a D on the last command, and that means that one's sitting in D. And almost always that means it's some sort of IO. And if you're seeing that all the time, then it means you're probably hung, and that would show up in the system time. Now, most of the time, especially if you have an MPI code, those will just be 100%, even if your code's not doing anything. MPI has something called busy waits, and so it sort of just holds that ready so that it's always ready to get data. So that doesn't tell you the whole picture, but at least it gives you some information and that you're at least running all the tasks and all the processes you thought you were when you launched that code, and you didn't mistakenly launch your program in a way that won't use all the processors. Okay. So these are just interactive commands. Another useful tool is the job perf command. So job perf is a SciNet specific command. If you have a job idea of a running job, you can take job perf and it'll give you a sample of what's going on with your job while it's running. So instead of you having to type SSH into each node, you can actually just type job perf and then a job ID of your job, and it'll give you some data while your job is running. So that's other sort of very low overhead, no changes to your code, nothing really different. You can just use that. Another useful thing, and a lot of you probably knows, is the SciNet portal. We collect statistics actually about your running jobs. And this is available for you to see. You can see the allocation details from your job, from your group. And then you can also see CPU usage, memory available, reads and writes. So I'm going to pull up a browser here. And I think, now that I'm not there. So there's our main site, and you can see the slides are listed here on the main education website. But let me switch to the My SciNet here. Okay, so when you log into My SciNet, if you go to, sorry, I'm just going to move this because this is hiding me. There we go. So you log in here, you'll see I'm logged in as myself. So I see this. There's my most recent jobs. Okay, and if I click on one of those, so this is just a sample. It's not a very long job, but you can see the general job statistics that you'll see in your slurm.out. And this is the interesting one here. You'll see some performance statistics. In our code, or on Niagara, we take performance statistics, but not that often, about every 10 minutes, because we don't want to take a lot of overhead in the system. But you can see the CPU for each of the processors running, and that's why they're different colors. And actually, you can click on here and you can see them. And you can also change it to memory that's used. That's memory available. You can see this wasn't using very much of the memory available. You can also see this tiny amount of file I/O done. You can see double provision floating points if you want to figure out this. And a lot of this in itself doesn't make a huge amount of difference, but you can see changes over time or compare different data. So you can see IB packets, so where the communication was. There wasn't as much as this part as there was later in the code. But even something simple as CPU usage, you can see that, okay, the code, all my cores were running, and I can see them all up at the same time. Okay, and so you'll see this overall percentage here. So this shows them information there. You could see the script that it was submitted, and then your environment at the time. So this is just nice just to have that job history there. You're basically getting this for free without actually having to instrument your code. And that can tell you lots of useful things about how well your code is doing, or how well, if you make changes to, can work too. Okay. So another way is to actively instrument your code. There's a couple different ways you can do this. You can do this yourself, and some of this is always useful if you have source code yourself. Putting in a little bit of instrumentation into timing how large or how much performance the different parts of the code take, it can be quite useful. So there's simple little like TikTok type calculations you can do, where you can say, okay, reading in the file takes this much time. You don't want to do this every iteration, it's too much overhead, but it's not a bad idea to build this in, or at least build it in so that you can comment it out, or put a macro so that it turns it on and off with pragmas. This can be useful just to kind of know over time how well your code does, or if you port it to a different platform, how different parts of the code take different times. So it's quite easily, we're just literally taking time, subtracting off the start time, and see how long each section takes. So this is self-instrumenting, and you can do various levels of this. And there's libraries that'll do this as well in various languages. But it can be a useful thing, just especially if you're an active developer of code, just to kind of see that data in your output all the time, so you know roughly how long each sections are taking. So that's quite another way to do. So self-instrumenting a code. Now, you're like, well, I don't want to do it myself. There's got to be tools to do this. And obviously there are. And that's what profiling tools do. The advantage of profiling is it's quite low overhead. You don't need to instrument it yourself. It's kind of like if you compile with -G, and we'll talk about -PG, which is the profile guided stuff. It will actually do this at compile time. And then when you run the code, it'll instrument different things. And you can do this with a couple different tools. And the first one we'll talk about is gprof. The disadvantage is it's profiling. So it's only going to sample at a certain rate. Now you can adjust that sampling. And in modern codes, that's not a problem. But what it really means is you don't know exactly, you're not going to track exactly every instruction sent. You're going to do sort of an averaging over time. What that means is you've got to run a significant, a big enough amount of work or through a specific number of iterations, not just one, to be able to sort of get a clear picture of what you're doing. Sort of, you're looking for that statistical average, right? So I mentioned one of the simplest and easiest ones to do, and it's built into most compilers, is something called gprof. And basically, just like putting in the debug symbols, the -G, you just add -PG. And what this does is this puts some instrumentation in your actual code. So when you run your actual code, it'll actually output a file giving you'll see this gmon.out file. And this will actually output a file that you can then analyze and see how well your code's done. And it'll tell you each function, which line the code had, and actually how much time it's spent in everything. So this is, once again, a serial type of thing, but it can be built in to a parallel code as well. It's just not going to have it as full-featured to sell the communications overhead that some of the tools that we'll get to later will. But it's still sort of the very easiest and simplest stuff to do. Now, you don't want to run with this all the time, kind of like debugging symbols, but it can be quite useful if you want to run it periodically to see where is the bottleneck. Is it in this function? Is it in that function? What line of code? I've never seen this code. I don't know which library it's in. You're not really sure. Okay, so that's a useful tool. Another one that's kind of like that, and I'll show some examples here. I've got some sample codes, and we'll get to that here in a minute. So you won't have to listen to me forever, but I've got some examples we'll show up here. I just wanted to show us a few of these simple tools, and we'll run some examples there to talk about them. Another one that's another useful one is so this is a gprof showing some output. All it's going to do is when you run gprof from that gmon.out file, you'll actually just get a bunch of lists of the functions. In this simple code, you're like, well, there's one main function. That's not very useful. Well, luckily, it will break that down further. If you give it the -line command, it'll actually break it right down, and it'll tell you what line of the code was spending all the time. And if we look at the line 82 and 113, dictation, no, there we go. You can actually see, not surprisingly, 82 is in the simple matrix multiplication, is just where you're doing your AX plus B type calculation. And the other one is 113 is when you're outputting to the screen. So, that kind of makes sense. Now, obviously, this is a very trivial example. In real world codes, the whole point is you're not sure where that's going to be, but this does give you some validation of where you're going to see some information. Okay, so let's go to the next slide. So gprof is really easy to use. It's pretty much everywhere. I said you can use it with the Intel compiler, the GCC compiler. It's fairly low overhead. And then there's also some tools that will actually, like kprof and stuff, which will show you that output as well. Normally, I just use it on the command line, and we'll show some examples of that because it's sort of the simplest way to use it, and I think it's good enough. Okay, so there's a few questions there. Yeah, sorry. Looks like Marcelo answered that. Sorry, I didn't have the chat window open. Okay, so another way to do is not just CPU. You also sometimes want to know where your memory's going, and this commonly becomes into a issue on systems when people, especially with lots of number of cores, is you're like, oh, I ran out of memory, and in SciNet we run into that. Now you have lots of nodes with, say, 40, 80 cores in them. You can easily exhaust your memory for the type of problem you're working on. And you're like, where is my memory? I don't even know. You kind of know some stuff is just going to scale with the size of the problem. But once again, if you're not familiar with the code, sometimes you want to profile it. So another useful tool is Valgrind. And Valgrind is a memory checker. Now, it does a whole bunch of things. It can check correctness to look for for memory leaks. It's very useful for that, but it also has this tool called Massif, which will profile your code and actually tell you where memory is being used over time. It also has a tool called cache grind, so you can see how much the CPU cache is actually being hit. This gets into some very detailed profiling, but the tool Massif, the nice thing about these, again, if you just compile your code with -G, run them, you can actually, it'll actually just profile the code, and actually Valgrind will work with parallel as well. You can go to our wiki, there's an example there. I can link to it probably on the next class of how to do that. And this is actually, you can actually run parallel codes to actually see where the memory performance is going to. So Valgrind is a useful tool. Now, it doesn't have the best interface, and it can be quite verbose, but if you're used to command line tools, it actually is quite powerful, at least as that first order without actually having to do a lot of overhead. So when you run it, it'll output an output file, kind of like gprof, and then you run this command msprint, and it'll dump some, these are its sampling steps, 11, 12, 13, and there's the time step, and then how many bytes, and you can see it changing over time. And then in here, if we look at this code, every time it's running, at malloc or new for changing memory, this is unfortunately a big C++ code, but you can see where it's actually called from. Oops, I'll click on that. And you can actually see what part of the code and what percentage of the memory is in that part of the code. Now, more complicated codes, this is can be quite tricky to follow. And there are better tools or more graphical tools and easier ones to use. And we'll get to those as well. But these are, once again, I think these are always good to know the basic open source tools that are available everywhere can be quite useful. So if you guys have access, you don't have to have this. We don't need to get in there and do this, but if you have access to Niagara, you can get in and clone some examples I've got. So if you log into Niagara in the login nodes, and then you can clone a SciNet course, Paraperform, or Paperform or Paraperform there. And then I've got a couple different examples there that we'll talk about and run these. One, we can go through here just on the simple diffusion code. Once again, these are kind of trivial problems, but they're just sort of to show you guys how to do this yourself, and you should be able to apply the same approach to codes you want to run. So I'm just going to pull up a terminal here. This is just on, yeah. So Marcel's saying, yeah, we don't have temp accounts set up for these ones, but if you'd like to try some of this, yeah, we can put those up on the website. Okay, so I've just git cloned this. The series of codes. There's just a series of codes. The one we're going to do is diffusion. Oh, I think it's, yeah. So then, yeah, we can. So yeah, this one is just module load, GCC. And I think I used pgplot on this one as well, but we'll turn the graph off. Okay, so then all I'm going to do is make, it's just a simple one-line C code, nothing too fancy about that. I think I've got a C and Fortran version, which is why in the make file there. But you'll notice that in the make file here, we've just added the flag -pg. So this is just the only real change to any code that you would have in Fortran or C, C++. You can just add -p to it, -pg, and then when you run the code, it runs this code. I think this is just it's going to run to 10,000 steps or something. Once again, this is just a serial code, but it would be the same thing for parallel code. You'll see at the end, you get this gmon.out file. Okay. So this gmon.out file, you can't read it directly. It's just a binary file, but it's all the instrumentation of, all the statistics and stuff when the code was run. But luckily, it's a simple tool. You just run gprof, the name of your code, division C. It's like looking at a core dump or something. And then gmon.out. And I usually pop it to less, and it'll just interpret it. So it's pretty flat. The first flat profile, you're just saying, well, not surprisingly, 100% of it was in the main function. Well, that doesn't tell me a whole lot. Not really, but in a more complicated code, it'll tell you which function. This is a simple code. We can look at the code, but there's really, it's just it's one from it's just one main function, which has a series of calculations for a 1D diffusion problem. So it's quite trivial from that point of view, from a sample code from an MPI course. But the nice part is if you run gprof again with the -- line command, now we can see, oh, okay, now we can see something a little more interesting. So now if we look here, I'm looking at 108 and 120 in that code, right? And I'm going to open up another tab. I'm going to make this bigger. I'll try to make this a little bigger so that you guys can see this. So let's, we were in diffusion. And let's go to line 108, I think it was. Yeah, so 108, not surprisingly, that's where it's a loop where we're doing a series of math, right? So an exponential function's in there, so that's not surprisingly where we're seeing some data. And then in 120, same thing. There's our step calculation here. What else we got? We got 87, 86, so that might be, yep, and more calculations here. Now this doesn't have to just be CPU calculations. This also could be, it's overhead from accessing memory as well too. But anyway, I think you get the point there. So it's a quite simple tool to use, low overhead, available everywhere, open source. So it's a good tool for that sort of thing. Now, another thing we can do is we can run the same thing. Now, this one, I think gprof, you don't have to load a module, but with, we have to module load Valgrind. Just to load Valgrind. This will work once again with GCC or ICC. You can use that with the Intel compilers as well. You can run Valgrind. So let's run the Valgrind command. So I think I even have it set up in here, but yeah, whatever. So Valgrind -- tool equals Massif, and then you run your. So run the same thing. Valgrind is instrumenting this as it goes, and then it's going to same thing as the Gmon. I guess I should have made this a little shorter, but I was just running it to the default. The one thing about Valgrind that you will notice is that the code will run a little slower. Valgrind is basically how it works is it intercepts every call to memory. Every time you do a new or a malloc, or you create memory or you touch memory, it actually instruments that and checks it. So in order to be able to do some of the low-level details, it sits in that layer between memory and your code. And so that slows the code down. You're like, well, that's going to mess with my performance calculations. Possibly, but you're looking at memory accesses. So you're not so overall worried about how long something takes. And as long as you compare apples to apples, like anything tested with Valgrind to anything within Valgrind or any changes, then the performance there should be consistent. But you're not really looking at overall performance like you are with the -PG for gprof. Here, you're actually just looking for how much memory you're accessing, so the actual CPU performance isn't as important. But Valgrind will slow things down, so don't be surprised about that. It actually is quite invasive, and it's important to know that if you're going to test your code, you don't want to run this on Valgrind on your production codes. It's really just there to test some memory checking when you need it. So now it's done. So then the command to do it is like gprof, but it's called msprint. Print, yep. And then we let me just try to do it the same. yeah, just msprint, and then if I can type. Then it just defaults to this massive.out file. And it gives a text output as well. Oops, what did I do wrong? Oh, name, of course. I think this starts with the PID of the, yeah. Okay, so it gives you a little text-based call profile. Once again, this is pretty trivial because it's a simple flat rate at the beginning, but it will show you over time. This was a relatively short, but it's got sample times, and it'll show you a series of snapshots and how much the memory changes over time. But as you scroll down, you'll see what we saw before. You have a series of time steps. You can actually see how many bytes, the heap memory that's available, and then where it's actually being called. So in this case, it's a simple, I think I screwed up and didn't compile this with -G on, so it doesn't have all the information. But anyway, you get the process here. There's lots of different, you can go to the valgrind.org and look at the man page, and maybe I'll show some examples next time on some of the more details of what Valgrind can do. Like all these, I'm only sort of touching the surface of some of these tools because I don't want to, I could spend a whole course on just any one of these tools. I'm just trying to do a range of various, options, and that they're available, and you guys are smart. You can go and find the documentation and find examples, or contact SciNet support and ask us, maybe I'm trying to profile this, but I can't see what I want. Can you help me? Maybe there's better options for that. I'm by far no an expert in any one of these as well. I've just found them useful in different circumstances. So this is the output of Valgrind. Once again, these are very easy to do, and they give you, Valgrind, it can be very verbose. Even something like the simple code, it gives you piles and piles of data that you can go through, and it will take a little bit of, digging into it to figure out, especially in more complicated code. But it can be quite useful for at least trying to track down different types of bottlenecks. Okay, so now we've gone through serial stuff. We've talked about instrumenting basic serial codes, looking for memory, system performance, even basic I/O by just looking at the system timing. And then you're like, well, this whole course was supposed to be about parallel, wasn't? I'm not quite there yet. I'm not going to get into, another thing I could spend a whole course on is compiler optimizations. For those of you, some of you are very familiar with this. You look at a makefile, you'll see different, what is O1, O2, O3? What are these X hosts? Why would SciNet do that? Well, this is all just how aggressive your compiler is when it goes to compile your code. Loop unrolling, different procedural optimizations. For Intel, we recommend just X host 03. What this does is it says it looks at the particular chip you're running on. On our case, our login nodes run the exact same CPU as the compute nodes. When you use that flag, it'll say, okay, just give me the best optimizations for this machine. This is the one I'm going to run on. You wouldn't want to do that in a production code, because then you couldn't take it might put some AVX512 instructions and vector instructions, and then that wouldn't work on your desktop. But in HPC code, you're usually almost always targeting it for a particular architecture. And so if you just use these flags, that'll get you 95% of the way there for performance. There are more details. You can do what's called interprocedural optimizations and profile guides, where it'll actually run your code. It'll give you some of that stats file, and you feed it back into it. And it says, oh, that's how we actually ran the code, because the compiler doesn't know how you're running the code. It just knows what the code's doing. You can feed that back into the code, and then it'll actually tell the compiler, oh, that loop is run 1 billion times. Maybe I should try a little more aggressively or pad it out to vectorize it. Okay. So the reason I put that in there is just, once again, this is more little optimizations you can try. Don't get too aggressive with some of these. Some of these you have to be careful of. They will change, like you can play with a floating point and details like that. But in general, I would stick to the Xhost 03. You can try and look in the man page and some other ones if you really want, but you're not going to have a huge difference probably in most of your codes. But it is important there is a huge difference between -00 and 03 though. I mean, it can be the order of 5 times difference of running without optimization and running with optimization. So nowadays that compilers are faster, there's no reason not to run with these flags almost all the time. And you used to be able to not run with -G and these flags at the same time, but now you can. Once again, people aren't as worried about fat binaries and stuff, so they actually do. You can run with the debug flags on and most of the optimization flags It used to before would be either or, which would drive you nuts because you go to debug a code and it works fine, but then you turn the optimizer on and it breaks things. Those are most of the good old days. Nowadays, there's no reason that you can't run both all at the same time. So just before I digress at the end of the serial stuff, I wanted to throw that in there because more than a few times I've fronted a few codes where people say, oh, my code's great, I don't need the optimizer. Well, the optimizer is doing different things than what you're doing in your source code. So why not use all of it to help run your code as efficient as possible? Okay, so what about parallel? Now we've talked for about 40 minutes here about various tools and various profiling. Let's talk about what this course is supposed to be about, is how do we do things, or how we approach things better in parallel. The problem is nowadays parallel means lots of things, and it means lots of things to different people. The one thing they have in common is communication. And communication, when you do things in parallel, we have to do some sort of synchronization to make sure we're in step. But different languages and different approaches do that very different ways. The two most common parallel approaches are shared memory, or threaded, which is most commonly done by OpenMP, where we can use two cores or two processes in the same node, and they can communicate through the shared memory, which is very fast, and it's coherent, and you can loop unroll and do things quite efficiently. If we want to do this across nodes, we have to use what's called a distributed memory. And the most common one of those is MPI, where I actually have to say, I have to synchronize between these two different processors to be able to do my calculation and stay synchronized. Now, if I have embarrassingly parallel workloads where I'm calculating two things, 1 to 10,000 and 10,001 to 20,000, and they don't communicate at all, then I can do that relatively easily. I don't need to communicate. But in most programs, in scientific worlds where you're breaking the problem up, you need to do some sort of synchronization, and you've got to be able to communicate that workload as you go on, and that's where the communications overhead comes from. And that's overhead that we don't want. And we're going to talk about that in a little more detail. So I've got a couple examples here. There are other distributed memory programmings. UPC and Core Fortran are part of the PGAS languages. These are partition global array storage. This is an approach to try to make MPI a little more palatable, so you don't have to actually send the messages. You just add an extra index in your array and access it as if it was local, and under the hood, it actually is doing the message passing. These are becoming more popular. They're still not super mainstream, but Core Fortran, you can program it in the Intel compiler now. It's part of the Fortran 2018 standard. In C++, in 17 and 20 and in 23, they're adding more parallel concurrent features in. There's OpenSHMEM and Chapel. These are Cray-based languages. OpenSHMEM is a version of the Cray-based languages that are popular. More and more, a lot of people talk about parallelism when it comes to GPUs. People think, oh, I'm programming on a GPU. Well, a GPU is massively parallel. A modern GPU can have 1,500 individual SM cores in it. So something like CUDA, you're kind of doing a thread-based parallelism. So you're doing quite a bit of communications in there. And a lot of what you're trying to do and how a GPU really works is all about hiding latency. The memory speed is way faster on a GPU than the actual GPU itself. How it gets a lot of its performance is massively over-threading what it's doing to be able to get that performance. And ROCm, which is an AMD version of the similar sort of things. There's OpenACC, which is OpenMP, threaded, sort of pragma-based approach. And then OpenMP itself in version 4.5 and 5 will also offload to accelerators. So it really depends on what you're talking about when it comes to parallel, which approach you can use. Now, luckily, some of the tools we'll talk about today, I'm going to mainly focus on MPI, because that's what we usually run into where we have the most access or control over the parallel performance. There's some good tools now, especially in the Intel tools that we'll talk about, that will go over some of the issues with OpenMP that you can dig into, and they become quite good at that. There's also some decent tools from NVIDIA itself, if you're into CUDA, like Nsight and their visual tools. I'm not going to really talk about those that much, but I'll point to them because I think those are useful as well. But the main we're going to talk about here is mainly MPI and then OpenMP. But MPI is really because when you're actively controlling the messages, you're usually that's the problem where you run into issues about scaling up. Okay, so I'm just going to quickly go through an introduction to scaling and throughput. commonly you would think this is pretty understood, but a lot of people jump into parallel programming or running a parallel code, and if they didn't program it themselves, they don't really understand fundamentally. They just assume this is a given, that if I run, well, if I have one processor, if I run 8, I should run 8 times faster. Well, that's the idealized case. That's not always what you get. So that's the idea of perfect scaling. Whereas if I had a person, that communication didn't cost me anything, or I'm not communicating, I just throw 8 times more processors, I should be 8 times faster for the same problem. And that's called strong scaling, where, I just literally have the same problem, but I just throw more work at it or more processors at it. I actually just speed up by the number, and that's perfect scaling. Sorry. In the real world, if we did that in terms of time, it's sort of an inversely proportional thing where my time drops off as 1 over the number of processors as well. So if it was taking 10 seconds with 1, if I go to 10 processors, I go down to 1 second. But obviously, this is going to run into a problem at the lower end scale when you start running a larger and larger problem, because if it takes 10 minutes, I'm eventually going to I might get it down to 1 minute, but eventually, even if I have a perfectly scalable problem or an embarrassingly parallel, but as I get smaller and smaller, I'm actually going to hit that part where I'm going to get some diminishing returns. But this, once again, we're focusing on the idealized case here. So if we plot it on a log, of course, we get the same sort of plot back here that we should see. We commonly talk about your parallel speed up, and that's basically just plotting the time for the serial. It takes on a serial code, so this 1. So if it took 10 minutes on a serial, then you just divide it by the time it takes on P. So if we did it on 8 and the time 8 was 8 times less, then of course the speed up would be 8 times. And ideally, we'd get this linear speed up. But in reality, we have what's called parallel overhead. You have some overhead at the top here. You partition the data. Then in the parallel region, this is where you're fully parallel, so there's no communications. And then there's some serial portion at the bottom here, some reduction, say some sum. We're adding all the numbers from 1 to 10,000. This is 1 to 2,500. This is 2,501 to 5,000. You get the point. But then at the end, I need to add them all up. Well, that's the overhead. And that serial portion blocks all of them at the end. So we're going to call that TS right here. And as you'll see, Amadel's law is way if we plot this serial portion, say that works if we can rearrange the equation here where T1 is the time of the parallel, TS is the serial portion. If we rearrange that, we can get this as a fraction of the overall percentage. So say 95% of my time, say I have a 100-second code, 95% time, 95 seconds is spent in the parallel portion, and 5% is spent, or 5 seconds is spent in the serial portion. As I scale that up, you can see the effect in the red line here that I'm going to plateau, and it doesn't matter how many more processors I take it, because as I go to 10, even if that idealized portion, I'm down to 9.5 seconds, well, I'm still doing 5 seconds for that serial part. So you can see that something that's only a small part can easily become a major component, and it affects your overall scalability. Okay. So this serial part very easily can dominate it. And you're like, well, but I need that serial part. How do I get around that? Well, the idea is to diminish it as much as possible. And it is true, it's a balancing act. But it's important to know in your code, especially if it's something that is part of your main iteration scheme. If it's something where just at the beginning you're reading in a data file, it's probably not too big of a deal. But if it's something you're doing regularly, this especially as you want to scale this program up to hundreds of cores, this vastly slows how or can affect how well your code will scale. So how to get around this? Well, one of the things to do is just to run a much bigger problem. When we talk about strong scaling, we talk about taking the same problem and then we just try to throw more processors at it. Commonly, that's not what we're doing in science, though, is because, yeah, okay, I've got a 10,000 node point, problem, and I'm running that on one processor. It takes me 10 minutes. That's fine. But usually, I may commonly want to solve, 10 of those problems. So that's fine. I can just run 10 of them serially, and that gives me better throughput. But what happens if I want to run a really large problem? Well, that's where our weak scaling problem goes, where I take the same a problem, say it was 10,000 points, and I go to 20,000 points, and I run it on 2 processors. But if I run an 80,000 point problem and I run it on 8 processors, ideally the same time would be constant for that, and that's called weak scaling. So it's not as difficult as strong scaling is, because the strong scaling, as you're actually throwing more communication and less work per processor. In weak scaling, you're keeping the amount of work you're doing on each processor constant. And so this is commonly referred to as Gustafson's law, whereas if you get a large enough problem, it can be efficiently parallelized, because basically that the problem is big enough, the amount of work you're doing on the actual individual processor would be significant enough. But really what this is just saying is you need to make sure that you have enough work for that modern processor to do that the amount of communication overhead you have is small, that it won't affect your overall scaling. And there's always a balance in there to figure out where that is. So, most of our science type problems take this sort of form, where the blue is on 4 processors. We have a series of parallel sections. We stop, we iterate, we do an all reduce or communication to simplify them. We do this in a series of loops. But the synchronization is our overhead, and we have to be aware of that, but we also want to be able to minimize it as much as possible too. Because otherwise this becomes our dominant F fractional cost. But so the synchronization, so this is why if you see an MPI, if you have collective operations, always get frowned on, because those inherently have barriers in them, because this one can't move on until they're all done. Another thing, and comes off right away at the top too, is load balancing. Is if this is the idealized case, where if I have 4 processors all running the process at the same time, I'll have the synchronization. But in this case, say I ran, on 7 processors and I have 8 tasks. Well, then one's going to be out of step, because these 3 are going to be waiting for that last one, because it's going to get extra work to do. So this is one thing that comes across on different compute Canada systems, because there's different number of processors per core. Traditionally, systems always had some sort of power too. So if you're on Graham or Cedar, they have 32 processor nodes. So that works out easily. I want to double it. I run 64, I run 28. But then you go to a system like Niagara, and our system nodes have 40 in them. So I want to run 2, I'm running 80. So how you partition your problem, you want to have that as close as much as possible to at least get some sort of benefit. Otherwise, you're just spinning your wheels, because you're basically giving more work to one processor than not the other. Now you can't always do that, but structurally you want to try to think to be able to make your problem, if you're asking for 160 cores, make sure that you're dividing it equally, not just trying to do 128, because now you're wasting those other resources. You want to be able to use it as much as possible. So this is where I emphasize load balancing, because the algorithms and how you launch your program, this will have a major effect on how just efficient. You're leaving performance on the table, not even looking at the code. Okay. Okay, so that's sort of my quick overview or diatribe about these main things. The main reason I wanted to talk about weak and strong scaling is this is one of the first things we'll ask you when you say, oh, my code doesn't scale. And you're like, what do you mean? Well, I ran it on 2 and I ran it on 4 and it just doesn't work well. Well, have you done a scaling study? What do you mean by that? Well, this is all it really is. Just taking a sample problem, doesn't have to be your full problem, but something significant enough, usually 10, 20 minutes of iterations, and running it. Run it on 1 processor, run it on 4 processor, running on 40. And then when you go off node, you might see a performance bump again, because now you're switching between, let's say there's an MPI code, between all the memory being communicated through the shared memory to over the InfiniBand. And having that data point will tell you your code. You're like, maybe it doesn't scale great, but maybe for your problem, it's better to run 40 core jobs and run 10 of them than run 1 job with 400 cores. And that's usually the case. And that's where that balance between strong scaling, weak scaling, and throughput, you're just trying to get your science done. I mean, if you're doing this as part of your research and you want to prove your algorithm, well, great. But a lot of the time, you just want to get your work done and get it done efficiently. Then balancing out that throughput and informants is more important and actually getting it through the queue than running the largest possible case. Because it's true, too, that if you submit jobs, you'll probably have a better throughput if you run 10 single node jobs that can backfill than 1 job that uses 10 nodes, right? So these are just things to be aware of, even just from how you submit your scripts, not even really even looking at the details of how the code is. Okay, so the next section now that we're going to get into, and this is the stuff you probably guys care most about, is performance tools. These are tools a little more, I guess, well-rounded and full-featured than the basic Valgrind and gprof tools, but they do the same thing. They're different sets of tools that'll help you look at, like debuggers, help you look at your code and figure out where that performance overhead is. Find out the bottlenecks. So we use two primary tools at SciNet. One is sort of like a linear map. It's actually called ARM map. I should change that now. Now they've been bought by NVIDIA, so it's different. But it's the same as the debugger, parallel performance debugger. And they have a tool called map and performance reports. And we'll show some examples of that, which actually look at your code and run and just look at the debugging information. You don't have, as long as you build with debugging, you don't have to do anything else, and it'll run your code, and you can actually see where the overhead is coming from in that code. The Intel tools. These come with any of the ICC and iFort compilers. And the good thing about this one is it is only Intel specific. And of course, you got to use the Intel tools and Intel MPI to use them. However, they have changed the licensing on this. And if I go, where's my browser here? Sorry. You guys can download these now for free. You don't need a license. We have the licenses at SciNet. But if you've got a Windows or Linux or Mac box at home, and this is for educational purposes, you can get access to these full sets of these for free. So I suggest if you guys want to use these to their best, and the thing about these ones, you'll get the compiler, but then you get vTune, Advisor, Inspector, and the MPI library, and all these tools, you can run them right on your desktop. And actually these tools work better on your desktop, especially vTune, than they do on the cluster. And there's some reasons for that, and actually has to do with we can't install all the low-level library stuff that you would on your desktop on the cluster because it really wouldn't work with the way we deploy the system. So, and also remotely, you'll see some of these tools work better. So go ahead. What I talk about here, you can easily do this on your desktop and have the access to those compilers as well. It's the exact same stuff we use on SciNet. It's just that some of these tools work better and sort of, they're really kind of geared towards a desktop environment. Okay, the ARM map, unfortunately, is a licensed product, and we have a license to run up to 64 tasks with that across everybody. So you would have to run that from SciNet. There are other ones, as I said, if you're doing GPU profiling, you can use the NVIDIA profiler. There's lots of good open source ones: Scalasa, Vampire, Tau, Open Speed Shop. We've played and had some of these installed over the years at SciNet to differing levels of success. There's lots of ones out there, and the good thing is they become much more parallel aware and have pretty good interfaces to them. But in this course, we're going to basically focus around Alinea Map and the Intel tools. Okay, and it looks like Marco Marcelo just put up the link there. So thank you for if you want to find the Intel tools and install them on your desktop. So the Intel Parallel Studio, as I pointed to on that website there, has the Fortran and C compilers, C++. Performance-wise, the C and C++ are basically, you're used to GCC, it's about equivalent. But if you're a Fortran person, you probably really want it. They have a very well-developed Fortran compiler and fairly modern too, supporting modern standards, which is much better than G-Fortran or G77 if you're really old, or old versions. But it's very full-featured that way. But we're going to be looking at the tools that they comes with it. And they've rebanded it a million times. It's called different things just when they're marketing, classic Intel marketing. But the one that is most common is called vTune. This is a tuning sort of performance suite. You can run the GUI or the command line versions of it. It's called Amplifier Now, and this is sort of your first hit. You run your code in. You can set up a little test program in there, and it'll launch and show you a series of metrics on even now on vectorization. It is also MPI aware. Inspector is it's kind of like their version of Valgrind, but once it's GUI, it's got a good interface, so it's good for looking at memory effects. Advisor is really good for if you want to look at your OpenMP, so if you've got a threaded code, or you want to look at vectorization. You want to see, how do I use those advanced vector instructions? You guys might have heard of AVX or AVX2 or AVX512. That's looking at loops and how well it can use those very specific Intel vector instructions to try to make your code faster. And if you can use those vector instructions well, so something like on Niagara, they have the AVX 512 that can do 32 operations and one step, which is, so theoretically you can speed up things massively compared to what you would do if you're not using those instructions. And it'll give you an advisor, basically, oh, if you make your stride in your loop 32 instead of 31, you're going to get some more performance. So these are really good tools for looking at that. The one that's specific to parallel is something called Trace Analyzer, or at least MPI. This is a tool which instruments your code. You run it just like we kind of do with you compile your code, or you run your code with a flag called trace, and then you actually it outputs a file and you look at it in Trace Analyzer. Okay. Oops, sorry. Do it again. The Intel MPI also has this nice check MPI flag where you can actually look for MPI errors, give some base statistics and collectives. And once again, these are just command line flags on the Intel MPI to actually, you can just do, and you can set some of these terms. And I'll show you an example of how we do that and how that can be helpful for finding something like a deadlock. Related to that, well, let's run that one. I think I have it later, but let's skip. Okay, I'll just skip through these quickly, but I have a better example later. So these are all part of the same ideas. If you can run the vtude stats by setting this environment variable, you run the MPI run code, you get the apps report. Same ideas like Valgrind. These are text-based ones, so they're really nice to just quickly show you like a call graph of where you're spending time in your communications. Trace Analyzer gives you a more detailed trace. You run trace with these are Intel MPI, and then you just run Trace Analyzer, and then it produces this .stf file, and it's a nice graphical interface like this, where you can actually see, okay, here I ran this 8 processor, or this one's 12 processor application. There's my MPI. That's this. What you want to see is all blue. Any red is overhead. So you can see this is the message passing, send and receive. These are all pretty quick, but then when I was doing this all reduce, so the Intel tools, as far as OpenMPI, they're really tied to Intel MPI. It's because if you can see how we're using, some of them will work with OpenMPI, but they're primarily built with Intel MPI, because in order to do the trace and the check MPI, they've been built into the MPI itself library and not something you're compiling in external. So you kind of want to, I usually recommend people have 2 ways to build their codes if you can. Use the GCC. You can also, now that being said, you can use GCC and Intel MPI. You don't actually have to use Intel and Intel MPI. You can also use, but it does, most of these tools are tied, kind of the Intel side of stuff, to the Intel MPI. The ARM DDT or tools that we're going to show later, those are agnostic. They'll work with pretty much any MPI and different platforms. So that might be a reason to use, and they kind of do similar stuff. But back to this one, the Intel Trace Analyzer, you can see here, the all reduce, as you can see, they all kind of wait. This one's done earlier, but then we have to wait for the whole reduction to be finished over here. Okay, so instead of, let's, here's some examples. Let's pull those up. And that we'll try to go through some of these examples. I think I have them. Yeah, so same deal, the pair perform. I've got an MPI, let's go clear this. Basic, oh, sorry. So I have an MPI basic here. Where is, so I think in this one I just have, yeah, so module load Intel MPI, and then Intel tools, okay? So it did some changes, module list. Okay, so that we're loading, oh, I've got Valgrind loaded, but it doesn't matter. We can make this. Okay, so I've got these ones called 3rd and 4th messages. And this is from the MPI course where we're looking for information, because this 3rd message, I'll show you guys this. See if you think with this very simple thing, all it's going to do is we're just trying to send a message. So we're using MPI blocking send with a blocking receive right after it. And all we're doing is, you know, if I'm on the rank 1, I send it to the other rank left, it's going the other way direction. So very trivial, simple MPI code, but it's a very common mistake people make. Well, I'm bearing the lead there, but there actually is a mistake in this code, and see if you can figure out what's going to happen here. So let's just try to run it. I go MPI-np2./third message. So I run it, and you're like, what's going on? Okay. I'm going to request to make this a little bigger, see if this works a little better. Yeah. So we've got a deadlock condition. You're like, okay. Well, now in this code, it's pretty straightforward to see because there's only 2 MPI processes running. But you're like, I'm not sure, what if this is my main code and I get that? And you're like, oh, now I got to sift through this. How do I figure out I've got hundreds of lines of MPI code? Well, if we go back to our, we can run the -check MPI. Now, you don't have to do these, but I'm going to run these export commands. This will just shorten up how long it waits. Otherwise, the defaults are quite long. They're like 5 minutes, and that's just longer than I want to wait. So I'm going to dump these two. There's a little check script that will run all these commands too, because I was, these ones, actually, we'll shorten them up even longer. 2, and we're going to run these to 5. And then we're going to go MPI run -check MPI -np2, and then third message. Now you'll see when this is a lot more verbose, it's telling you, well, here's some checking. I've got all these are the checks that are on. And then right here it says check message errors. And then, okay, so now I've built in this time, I've set these short. And then it craps out right away and says, oh, look, I've got a global deadlock fatal error. Here's where it happens. MPI send. That's because of the case where I've got this, you know, basically, let's open up that code, third message.c. I've got this case where the send goes one way, but I'm not going to be able to hit that receive to move on. So I'm going to end up in this very classic deadlock case because these are blocking sends and receives, right? So for those of you that have taken the MPI course, the way we get around that is, let's go to fourth message, is we have to check if I'm the first processor, I'm going to send it. But then if I'm not the first processor, or I'm basically the evens and odds, I'm going to receive first and then send, right? So that's our way around that. So now I'm going to run the same command, but fourth message, and works fine. So this is quite nice to throw on. Just if you're developing code, just leave it on because you may pull up, and there's different, you know, checks it'll do along the way. And it's kind of a nice little thing. Once again, this is tied specifically to Intel MPI, but if you have it, there's no reason you can't use it. And then OpenMPI has some things too, but not to this level. It has some checks which will take line outputs and some details like that. But this active checking is really one of the sort of the value addeds that they've added into Intel MPI over something like MPICH. Okay. So that's a not really a tool thing, but I think it's a useful thing to point out, or profiling, because it can help you with your development cycle. Just, you know, find errors quicker. That's usually, finding the error is usually the most difficult part. So then another example I have in here is, okay, we can go to I have one called in the heat equation. Heat equation. So if you look in this Intel trace options, I've got some sort of cheat sheet examples here, which are basically the same thing that's in the notes there. But basically for VTune, if we export, if you do a manual search for the Intel MPI, you can find what all these individual flags are. And unfortunately, it depends on which version of Intel MPI and Intel tool you're at. They've changed them quite a bit, unfortunately. But for this version, for 2019, this works quite well. Then by flagging that, setting that 1 to 20, which means basically tell VTune to record everything that I'm going to do. Then if we run this command here, we're going to run just 4 processors with this. Oh, did I build it already? Oh, I haven't built it yet. So this is still with the just using all the Intel top to bottom here. I export the stats, then I can run this command. So running basically just the standard, just like you'd run a regular MPI, but we've turned on that flag. That's telling vTune in the background to say, hey, I'm gonna record a log of what you're doing here. If it works. Maybe I should have slightly smaller case, but I'm only on the login nodes too, so I might be running interference. Okay, so it ran fine. I've turned off all the I/O, so just because, well, not all the I/O, but at least the command line I/O. It's another simple heat equation type problem, simple 1D thing. We output some data files at the ends, but primarily it's just looping 10,000 times. And at the very end, it conveniently gives you, hey dummy, you can output this little file, and it'll give us a report, which is quite nice. And it's all very similar to gprof. It's just a text report. You can get it in HTML too, but it's much more convenient just to look at the output. So we can look at the overall time was 16 seconds. How much time did I spend in the MPI? I spent just under 2 seconds, or 11.8% of my time here. In those top MPI functions, where did I spend all my time? Well, all reduce and send receive. Imagine that. Once again, this is a very trivial case, but this is the type of thing where you can get the statistics. You can see if there's disk I/O bound. It'll check some of the stuff, and it's very easy, as you can see. Run quick analysis, maybe not full detail. We have more examples there, but you can actually dig into this quite easily. So that's quite nice. Okay, so that's just simply by setting that MPI stats. Now, I warn you, running each of these commands that I have, they're not all play well with each other. So I'm going to unset. You can just load up a new shell, these variables, because they don't all play well with each other. So you kind of have to pick one or the other and don't mix them all together. And that's why I kind of have them in the run script there. Okay. But it is quite nice, for doing quick. I like quick responsive command line tools because as I'm developing things, I can see something really quickly. This is stuff that I can easily build right into my make file. Make MPI check. I used to do that with my profile guided stuff. I'd build profile right into all my tools so that I can build, just like building a clean, I can run these commands regularly as I'm building things to find, issues. And a lot of the stuff you don't even have to recompile. It's just a matter of a series of flags that you have to pass to it. Now, admittedly, I don't remember all the flags either, so that's another reason to bury them in your makefile. Figure them out once, and then build them into your workflow. So the next one we're going to do is, where do we got here? We're going to run now trace. So this is going to set up. It's going to run, and it's going to generate a trace, kind of like the vTune with the APS files. But this is a slightly different, more involved tracer, more like what we got from it's like gprof, I guess. But we're gonna run this again, and now you're gonna see in the directory you'll get a whole bunch of .stf files. I guess it stands for tracing file, but this will run for a few seconds here. And again, you can run this for 4, 8, 10 processors as much as you want. We ran the same thing, but see now you can see it's tractor cluster info, and then it writes a series of these ones of files. Now, if we look in the directory, we'll see all these it's really messy. You'll get a pile of STF files. They're not really readable from the command line, but luckily now if you load up the program called Trace Analyzer, it comes with, now this might be a bit choppy because I'm doing this over X. As I said, that's why these work a little bit better. You can always copy these files back to your desktop if you have them whole too, but the Trace Analyzer luckily is pretty lightweight. So all we do is we go open. That was the last one I was doing. So let's go back to where we were doing MPI heat equation. So then there's a top STF file. We pick that one. We open it up. And the first screen it'll show us is it'll give us this sort of very similar to what we had from the vTune text-based analysis, where it's saying, okay, what are we doing? MPI calls is 10.9%. Serial code, you're like, serial code, well, that's the part that's running in parallel, so that we want to see mostly blue. So it's running 4 serial codes is the way they see it. So 4 processors, 1 node, total time 65 seconds. Where are we spending all our time? 5 seconds in MPI send receive, a little bit in finalize and reduce. That's no big deal because we're only calling them once each. Okay, so that's kind of good. But sorry, I'm just going to move this out of the window. So that's sort of that top level. And then the next one, it jumps in, and this is where we can drill down to see what we're actually seeing. So you kind of have to play with this a little bit because the interface is a bit chunky. You see group MPI, hit show advanced. What it'll show in here is time that you've spent. This take a second here. This said running interactively X. So weighted barrier. So overall time. This is where we're spending 2.33% of our time as overall waiting on barriers. And you're like, well, then it actually gives you some nice little commands, or if you're not familiar with it, what an MPI barrier is and what's going on here. And what you can do is go to charts and you go to event timeline, I believe. This is the one you want to see. And this will be similar to that plot that I showed you in the actual slide deck. So we have 4 processors here, P0 to 3, and this is all this little iterations are all the communications. You're like, I can't see anything. Well, just like a debugger, if you just zoom in on one little section of it, we're running a series of iterations, so the communication is all pretty constant. If you just keep zooming in, you can zoom in on basically, or only run 10 iterations. You can kind of see your communications pattern, where we have a series of MPI send receives, right? Between each one. We can zoom right in on that. And the time that we're waiting between each one. So senders, and then it tells you weighted barrier, and then you can see what's going on because this is the end of an MPI reduction. So this is the send receive, and then there's a reduction, and that's why they're all going at the same time here, because even though this one's done earlier, it has to wait for all of these ones. Now, you can see for this code, it's actually pretty good, especially for something that's in 1D. But I'm on 1 node, I'm only using 4 processors. Obviously, as if I run this up, this is not going to scale well for this particular type of size problem, right? So that's kind of useful. There's other charts in here too you can mess around with. As I said, you can play around with qualitative. Oops, Apple's jumping up. Stop it. Yeah, and then you can also, there's some projects, you can save this as a project, compare it to another change later, so you can actually look at changes over time. What else is useful? Down here, there's a load balance profile. You can kind of look at that too to see, how many calls. This is all just looking at the stats. You said you kind of have to get in there and play around with yourself. Once again, this is a pretty trivial code, but it should be relatively, quick for you to figure out where the overhead is, because it'll be pretty obvious in a few handful of calls. What else is there? You can write an imbalance diagram where you can run what it does is it runs the program in an idealized form, and then you can compare sort of a baseline case and see if you've got better or worse to changes you made. So say you had a code that was all, you had a mistake and you had lots of extra barriers, then you took the barriers out, you could compare the 2 of them inside that, okay? So I'm gonna quit that trace analyzer, okay? Okay, we're gonna leave the ARM stuff. I'm gonna show you just a few more examples, and then we'll finish off for today, because I think we'll leave the other stuff to come back on Wednesday. We'll get into the ARM map examples and map trace, and then also some more details with these Intel tools. I will show you quickly some of the other tools you can launch, just because I think this is I don't really want to get into them because they're not as much as part of this course, but this advisor one is interesting, and this amplifier XL, and you can run those right from as soon as you load so let's go to, I've got an OpenMP example here, which is kind of just a simple, because I haven't talked really about OpenMP that much. It's just simple, literally a series of 3-dimensional loop over that's been OpenMP'd or threaded, right? So that supports that. It's a very trivial case that way. But say we wanted to see how the effect of that vectorization and the threading, we can open up and buy GUI. As I said, the best way to do is just load these up and play around with them, because their interfaces are pretty straightforward. And Intel, being a commercial product, actually has fairly good documentation on this stuff. So it's fairly intuitive. I mean, if you use one, you can see it looks very similar. All their tools have a similar sort of look to them. So we want to file, new project. So we're just going to call it test. Create that project. Okay. So we're going to start. This might be a bit slow. So, as I said, that's where some of the stuff works better if you're working on your desktop, but it will work. It's just, what's going on here? Or maybe it won't. I think it's hung on me. Of course, let's kill that then. Let's try this again. Some of the graphics sometimes gets this Java base, so over X, sometimes things get a little bit wonky. The trace analyzer is pretty good because it's got a pretty low end interface. But what we'll do is we'll just go to the other one I had already created a project. Hopefully that one will work. So I can say show my result. This is where you just basically run start survey analysis. It works the same way as the trace analyzer. It runs a sample of your code, and then it'll give you some feedback basically on different parts of your code if this ever runs. I should have installed a local version, but I don't have it set up right now. It's being, of course, live things, they always don't quite work. They work. Okay. Oh, here we go. Finally showed up. There we go. So you can run, so let's go to summary, vector advisor, start survey analysis. Let's see this run. Unspecified. Collect. Why is it not there? Okay. I did something wrong. Okay, well, I'll set this up. We'll show this at the beginning of the next class because I don't want to waste your guys' time. I'll get this sorted out. We'll start with showing this one at the beginning of next class because I think I broke something. Anyway, okay, so let's can that one for now. Yeah, so if you guys have any quick questions, we got a few minutes here about what I talked about. As I said, next class, I'll start with some of these Intel tools to show, I'll have some examples there. Then we'll get into the ARM software as well, and then show similar examples there. And then also I want to get into some differences between blocking and non-blocking messages, some examples there, show a little more details about the type of problems that you would want to run into or how you could get around. We found the bottlenecks using these tools. What are different ways I can do to reduce, parallel overhead, possibly. Those are MPI cases. And there's also, I got a CFD code which shows different types of, it's a 2D problem, a little more realistic, still kind of a toy problem, but still calculations to show effects of different types of MPI communications as well there. And then I'll show this OpenMP one. If you guys have any questions, feel free to turn your microphone on and ask away, or if there's something you would like me to add on or talk more specifically or reiterate for next week, I can do that too.
Hello.
Oh,
wondering if my mic works. Okay. Thanks for the presentation. It's not so related to these Intel tools, but I have a question about how to run sort of smaller scalability studies on a single node.
Okay.
What I encountered was at the beginning, I was trying to do like running my code on one core and then 2 cores and 4 cores. But the fact that like the Intel Turbo feature changes the clock speed of
Right.
the,
Right.
depending on how much load you're putting on, made my scalability plots look really bad.
Yeah. Okay.
Is there a
Yeah.
way to get around that?
There are, let me take a note. I know how to do it from the BIOS, but how to do it from user space is a good question. So for those of you who guys don't know, modern processors, because they have so many cores, what they do is they can, used to, you'd say you have a 2 gigahertz processor. Well, it would always stay at 2 gigahertz. These modern processors say, oh, look, you're only using 2 cores. Well, I can, in thermal and power, I can run this speed up to 3 gigahertz. And we usually want that because then you're using the processor more. But when you're running a scalability test, now I've got this artificially inflated number because when I'm running 40, obviously I can't run, it's running at a lower clock speed. So a kind of a hacky way to do this, it's not the best way to do it, is you actually run 40 of your serial processors at the same time and take that as your baseline, right? So then you're not getting the effect of, so on one node, you literally run 40 copies of the serial test case. Now, it depends on how much memory you're using, but that'll at least simulate the fact that you're not competing. You're competing the same as if you were when you're running fully loaded, right? So I'll see if let me take a note here and see if there's a way to turn off the turbo in user space to not be able to do that. Because you're right, otherwise you can't ever get that you're not your serial case isn't really representative of what you get when you run the full node. But as I said, a workaround though is you can run 40 of your serial case for 2 processors, run 20 and that sort of thing. But then you can run into memory issues too. So it's a little tricky to do right down to serial. The other way to do this too is depending on how large, I guess you're talking about primarily single node cases. But if you're running multi-node cases, like you want to run a big MPI case, you can do it, just scale it to the node. So 1 node, 2 node, 4 nodes, so you're dividing by 40 in that case.
Yeah, the way I did it to get down to 20 cores was I just assigned MPI process to a single socket, I guess. There's a command that seemed to work, but
yeah, you
start
can
at 20.
Sure, you can tie it down to the individual socket, and you can do there are some flags for like the threads and stuff. Was this an MPI code or OpenMP or?
It was OpenMPI, yeah.
Yeah, MPI. Okay, so yeah, you can tie it to that. But as far as how the processor is handling it, the thing is too is memory bandwidth changes too, right? When you're running with one processor, you have available all of the memory channels. When you run more, you get less, right? So it is a little bit trickier. As the processors get smarter or they try to do higher performance, they're not everything is exactly with the one full, that simple as like our idealized plot that I showed earlier. But I'll take that offline and see if I can figure if there is a way or some flags with the Intel to sort of emulate not going past the base clock speed that you'd get from when you run a full node. It was a good question. So there's a question here in the quotes, what's the difference between NSITE and NVProf? Well, luckily I did attend GTC, and if we do a quick, let me, NSITE, NVIDIA. So NSITE, they just rebadged their naming convention on some of their tools. Because NVIDIA has HPC tools, but they also have graphical tools. And so now they've kind of broke it into different pieces. So they have the visual profiler, which is sort of the top level. And then they have 2 different sort of starting profile levels. NSITE systems, which they've got compute, which is more for us who do compute level stuff. And they've got their graphics and they kind of want to pull it all together. Basically, NSITE is just the newer version of NVProf. As you guys who work with GPUs know, every version of CUDA, they change around this structure as they try to build out a bigger and bigger ecosystem. And they've just released it. They've got their own, top level compiler too. So it's just, it's all, if it starts with NV or any of the N terms, that's all NVIDIA tools, but it will change between which version you've got, which version of CUDA you're working with. Is there any other quick questions? If not, I think we're going to leave it there. I've got a few notes that I'll try to fix up for next time. If something comes to you and you think about it, please just email us at SciNet or myself directly, just Northrop@SciNet, and I'll try to add it in for the next course. I think we're probably only going to go, unless we get really bogged down, I only have sort of enough material to go to the end of Wednesday. But if there is some other more topics, I'm happy to go through Friday as well. But just if you guys are planning your weeks, we'll probably just have one more session on Wednesday at 12:30 to 2 as well. Okay, if that's it, I'm going to end the time here, and we'll talk to you guys on Wednesday. So thanks for listening.